Hello and welcome to the sixth lecture on General Concepts in Organic Chemistry GCOC. In this lecture, we shall be talking about the relative stabilities of carbocations and carbon free radicals. You must be wondering that we have talked a lot about carbocations and free radicals. But in this lecture, we shall use all our knowledge of all the electronic effects, the three electronic effects that we had studied. R effect, that is M effect, resonance, hyperconjugation, H effect, and I effect, inductive effect. All will be used to order all types of carbocations. And also, we will order all types of carbon free radicals. So a composite list will be prepared and the logic discussed. Once again, it will be almost a revision program, but still something new you will find. Let me bring my pen. Color. Yes, I like this color. Now you already know that alkyl carbocations, 3 degree, 2 degree, 1 degree, methyl, all these carbocation stabilities are explained best or predominantly by hyperconjugation effect. Although in some cases plus I effect can be used to explain, but the actual cause, the main cause of this stability is not plus I effect, it is hyperconjugation effect. Have a look. In case of 3 degree, 2 degree, 1 degree and methyl, which is also 1 degree, you can explain through number of hyperconjugation structures. 3 plus 3 plus 3, 9 alpha hydrogen. So 10 HC structures. Here 7, here 4 and here none. But also you can explain the plus I effect. Ignoring the H effect, you can use plus I effect to explain the trend. But what will happen when you are asked to find the relative stability between isobutyl carbocation and ethyl carbocation? If you use plus I effect, this has a greater, isopropyl has a greater plus I effect than methyl. So you will say that isobutyl carbocation is more stable, but actually ethyl is more stable. Why? Because hyperconjugation is the main cause. Here there is only one alpha hydrogen atom. And here there are 3 alpha hydrogen atoms. Hence the number of sigma p conjugation. Hyperconjugation structures will be more here in the second case, and it is more stable. So you must remember that hyperconjugation is the actual cause of the stability of carbocations. Now, you also know that species like benzyl, allyl, and this one is a new species that possibly I have not talked about. It is propargyl. Prop to vinyl carbocation. This has, all of them have resonance stabilization. But because this carbon is sp, having more electronegativity, and that will, when the negativity will be more, so the minus I effect will further destabilize this propargyl carbocation to the extent it is less stable than allyl. But we will see when we will grade them together, we will find this will be more stable than ethyl, propyl. So in ethyl or propyl there is only hyperconjugation. But here there is resonance. So propargyl will be more stable than ethyl. Hold on. And similarly, the acyl carbocation is also stable. You must remember it is as much stable as a third butyl carbocation. Tert butyl is due to hyperconjugation. A lot of hyperconjugation structures, but acyl carbocation is due to a resonance. You can draw another more contributing, more dominant RS by electron delocalization. I am not drawing the RS. You have mastered over drawing resonance structures. We are not going to do once again here in this lecture. Now see, alkyl compared with vinyl and ethynyl. What is the cause? This is sp2 carbon, vinyl is sp, and in ethynyl it is pure S. So more is the S character, more is the electronegativity of the carbon atom, and the positive charge will not be happy to stay on a more electronegative atom. Rather, it will be happier to remain in a less electronegative atom. Therefore, alkyl carbocations more stable than vinyl, vinyl more stable than ethynyl. We'll be putting all of them together to make a composite list. Now see, this I have not yet discussed. This is called the bent bond resonance or bent bond theory. Now cyclopropyl methyl CH2 plus. It has also high stability like allyl. Now this stability is due to a kind of resonance, a kind of delocalization which is analogous to hyperconjugation effect. Now this is a highly strained cyclopropane ring where this CC bond is rotating, and this CC sigma bond, this C sigma bond at some time come parallel, nearly parallel, cannot be exactly parallel, come to the near the same plane with the empty p orbital and can undergo a kind of sigma p overlapping to form a stable molecular orbital. So because of this, this is called bent bond because this is a bent bond and there is an electron delocalization with a p system. Whenever there is a p system, it will be called a resonance or hyperconjugation. Conjugation term will be used. There is effective overlap between the vacant p orbital of the carbocation with the ring carbon-carbon sigma bond, bent bonds or banana bonds, sometimes it is called, in the highly strained ring. The CC bonds here conjugate with the p orbital and it can be considered as an extension of hyperconjugation. So because of that, cyclopropyl methyl carbocation is stable due to bent bond resonance. And if you put more number of cyclopropyl rings to the carbon atom, this is tricyclopropyl methyl, dicyclopropyl methyl, this is cyclopropyl methyl. Obviously the stability will be more as the positive charge will be more delocalized in the three directions of the cyclopropyl ring. Got it? Now, aromatic carbocations is a separate category. About aromaticity, we have not yet produced the video. We'll be doing shortly after few videos, a couple of videos. Aromatic positive ions, carbocations are extremely stable. You know, aromatic species, whether it is a positive ion or a negative ion or a neutral molecule, those are highly stable because of a special aromaticity feature. We'll talk about that later. Now that will be explained by Huckel's aromatic theory, a rule of aromaticity. We'll not discuss here. Now cyclopropanium ion and tropylium ion, that is cycloheptatrienyllium ion, they are extremely stable due to aromaticity. Now these things you know, pattern 3, positive charge next to a heteroatom like nitrogen or oxygen is called oxocarbenium carbanium ion or carbocation. This is called, iminium ion. This one, iminium ion. These are more stable than their non-oxygen and non-nitrogen counterparts due to resonance stabilization in the former. That is pattern 3. You can draw the other more contributing RS to explain the stability of carbocation next to a oxygen or nitrogen atom. This is oxocarbenium ion and this is iminium ion. Now I'll tell you that the relative stabilities of carbocations are nowadays determined experimentally by a phenomenon called hydride ion affinity energy, HIE. Because when a carbocation plus charge will be accepting a hydride ion, a negative charge, it will form a corresponding neutral compound, and by that it will release some amount of energy. More the amount of energy released will speak about the less stability or instability of the carbocation. If the carbocation is more stable, then it will release less energy. If it is less stable, it will immediately react and will release more energy. So from the HIA data, we can order all the carbocations in the decreasing or increasing order. And earlier, the gradation was done on the basis of SN1 rate. We will not talk about the nucleophilic substitution, that is first order. That SN1, any organic substrate is subjected to SN1 process where the carbocations will be involved, and we find the relative rates. More is the rate of SN1 reaction, more is the stability of the carbocations. And that is not a very reliable and dependable tool for all types of carbocations, because many do not go via carbocations or via SN1 mechanism. Therefore, hydride ion affinity values, they give a dependable idea about the relative stabilities of carbocations. And also addition reaction with HX. If there is a double bond in that particular compound and you take an alkene and you add HX, HCl, HBr, HI, that also goes via carbocation, electrophilic substitution, electrophilic addition mechanism. That also we won't discuss here. And the rate at which the reaction proceeds, that also will give you the relative rates of relative stabilities of carbocations. And in many literature you find the order in the stability of carbocations do not match. This might be due to, in some places they don't match. For example, many authors, they say 3-degree carbocation, tertiary butyl carbocation is less stable than benzyl. But I will say, but not only I, but also many authors, they say that third butyl carbocation is more stable than benzyl. And this is supported by HIA data. Now I am giving you, thanks to Google, from which I have borrowed this data to show you that benzyl is more stable than benzyl. Where is benzyl here? This is, carbocation and HIA, hydride ion affinity energy in kilocalories per mole. You find this is aromatic. Tropylium ion is the most stable because it has the lowest HIA. Then triphenyl methyl, I'll show you the structure. That is second. Then cyclopropanium ion, that is again aromatic. Then diphenyl methyl carbocation. Then forget about norbornyl. This is tert-butyl carbocation, which is convincingly more stable than benzyl. This is 234, this is 231. Then isopropyl. Then this is cyclopropyl methyl, bent bond resonance, which is less stable than isopropyl, but more stable than allyl, convincingly more stable than allyl. Not because benzyl has a resonance stability and tert-butyl has hyperconjugation stability, so resonance is more dominating than hyperconjugation. So you just, without any supporting evidence, you presume that benzyl is more stable than tert-butyl. It is a nuisance. You know, there are so many 9 alpha hydrogen atoms. So the cumulative effect, the sum of all the hyperconjugation structures, that cumulative effect is more powerful than the resonance contribution in benzyl. Now then comes, this is, forget about this, is cyclopentadienyl carbocation, and this is propargyl. I told you propargyl is more stable than ethyl because there is some resonance here. Although resonance is slightly, countered, opposed by the sp nature of this carbon, but despite that it is more stable than ethyl. Then vinyl, double bond, and then phenyl. Finally, this is methyl carbocation, but below methyl comes this one. Remember, this is ethanyl. See, vinyl is 287, methyl is 314, and ethanyl, which is coming below methyl, is 386 kilocalories per mole. Therefore, we make a composite list. I will talk about these things little later. We have made a composite list containing a few known and familiar carbocations which are always found in examinations. The number 1 is tropyliumine, aromatic. Then triphenyl methyl carbocation, so many resonance structures, 3 plus 3 plus 3, 9 plus 1, 10 resonance structures. Again, this is aromatic. You might wonder there is only 1 or 2 aromatic, resonance structures, but resonance is not the actual cause of the stability. It is aromaticity, which we won't discuss here. So aromatic, this is aromatic. This is much more stable, and its HIA value, the HIA of tropyliumine is the lowest, meaning thereby it is the most stable carbocation. Now, cyclopropanium aromatic, this is diphenyl methyl, that is still a lot of resonance structures. Then tert-butyl. Tert-butyl is similar to acyl. Now I will be bringing my pen. Yes. This is tropyliumine, triphenyl methyl, then aromatic propanium, cyclopropanium, this is diphenyl methyl, this is tert-butyl, and then which is same as acyl. Then comes benzyl, tert-butyl, then benzyl, then isopropyl, 2-degree alkyl, then cyclopropyl methyl, then allyl, then cyclobutadienylium. This is anti-aromatic. You will be talking about that later, which is less stable. That is why it is less stable, although there are resonance structures. Then this is propargyl. There is some resonance, but it is opposed by the sp electronegativity of this carbon. But that makes it more stable than ethyl. Then ethyl is more stable than vinyl. Vinyl is more stable than phenyl, which is in turn more stable than methyl. And finally, the least stable carbocation is ethynyl carbocation. That is all based on the practical HIA data. Now, the things which we didn't discuss, which now I am saying, these are the three common factors which affect the carbocation stability. These you know. These are not unknown to you. First one is the number of adjacent alkyl groups. That means more is the degree of substitution at the charge center, more is the number of hyperconjugation structures. So 3 degree greater than 2 degree greater than 1 degree and greater than methyl. So adjacent carbon atoms, so this is plus, hyperconjugation effect is the main cause. Then adjacent pi bond resonance. If there is a pi bond next to the positive charge, away from the positive charge by one single bond, then it is resonance, allyl and benzyl. And third one is the lone pair resonance stabilization. Positive charge next to a heteroatom. That is iminium ion. This is iminium ion and this is oxo. You know, you draw another one. We have not drawn. I think it is injustice. In one case we have drawn and the other case we haven't. So this is injustice. I am doing justice now. So because of this is stable adjacent heteroatom. So these are the main factors. Let us now see why this carbocation is more stable than this, because it is allyl. Is resonance. This is simply hyperconjugation of 2 alpha hydrogen atoms. And this is again allyl. This is non-allyl. This is benzyl. This is non-benzyl. This is double allyl. This is single allyl. You got it? Need my thick pen? Yes. And here this is iminium ion. It will have another RS. There is nothing here. And there is a oxocarbenium ion. There is a nothing here. So undoubtedly this is also oxocarbenium ion. So there is nothing here. So all these things you can understand very, very easily, and in your examination can identify which one is more stable. Now this you know, allyl carbocations are stable by resonance, and if it is further substituted at the positive charge center, then due to hyperconjugation it is still more stable. This is 3 degree allyl. Allyl but 3 degree. 3 plus 3, 6 alpha hydrogen atom. This is 2 degree allyl and this is simply allyl. So both resonance, the common factor, and the hyperconjugation, there is no hyperconjugation here. So that makes 3 degree greater than 2 degree greater than 1 degree. Now coming to, I just identify which are really very, very less stable carbocations. And among them comes the highly strained ring, that is bicyclic ring, and the positive charge lying on the bridgehead carbon. That positive charge will make the entire ring unstable, which therefore it is very, very unstable, because that will necessitate, the sp2 hybridization demanding planarity. So that can't go to one plane, so it's unstable. Similarly, vinyl sp hybridization, ethynyl pure s orbital, and phenyl, which is less stable than vinyl but more stable than ethynyl. We have done it. These are, in fact, our impression about these are they are less stable. And this order, composite order, we have discussed. Now, just for fun, I have given you a data where a carbocation can be kept alive for years together. It is available in the form of a salt, stable salt called crystal violet, where a carbocation is there. It is not a reactive intermediate, it is there, a live carbocation. And it is not a surprise to you now that why this carbocation is so stable that it is not dying. It is because it is not only triphenyl methyl but also supported by the para amino group, dimethyl amino group, where nitrogen has a lone pair which will further conjugate. When you draw the RS in a particular ring, when the plus will come here, there will be another RS, that is the pattern 3, the lone pair adjacent to positive charge, and that makes the carbocation so stable that it exists even as a stable salt, chloride ion, and this the corresponding bulky cation. Now, in a reaction, you must also know that when a carbocation will be formed, I'm introducing this to you because that will be used in a separate program. Whenever a carbocation is formed, for example, you add HCl, HBr, HI to a alkene, then this will act as a nucleophile, the alkene. Alkene will be behaving as a nucleophile and HCl as an electrophile by donating a proton. But the hydrogen, if added to this position, carbocation will come to this position. On the other hand, if hydrogen bonds to this carbon, then the carbocation will come to this position. Now, if you compare between the two possibilities, here this is a 3-degree carbocation and here it is a 2-degree carbocation, which is much less stable than 3-degree. Therefore, this is not a possibility. It doesn't happen. It happens in this way, that hydrogen is added to the other carbon so that the plus charge remains on a more highly branched carbon. In this case, it is 3-degree carbocation. Similarly, if you take a diene, a conjugated diene, then you have added one H plus. If H will be joining here, plus will be coming here. And by that, again, it is a stable allylic carbocation. But if hydrogen will be joining here, and plus will be coming here, it will be an unconjugated, it's not an allyl, it's an unconjugated 1-degree carbocation, which is less stable. So such thing does not happen. This thing happens. Similarly, when you have a methoxy group and where this is a plus M or plus R group, then if you, supposing this is a carbocation, isopropyl carbocation, if that you attach it to the ortho position, then the positive charge comes to this position, which is adjacent to O. Pattern 3 is now applicable. So this will be further stabilized by the delocalization of the lone pair on oxygen. Right? But if it goes for a meta attachment, if it attacks the meta position, then the plus charge will come to the ortho position, and you can draw another 3 resonance structures. None of them will carry plus charge adjacent to oxygen atom, and the lone pair resonance stabilization pattern 3 will not be possible if this carbocation joins in the meta position. So it has to join in the ortho position rather than meta position. Not only ortho, you will also see same will happen if it joins in the para position, and you draw the resonance structures. You will find in one of them the positive charge is coming adjacent to oxygen atom like this. If it in para position, plus will come here, then another RS plus will come here. But if it is a meta position, you go on changing the pi bond, get the 3 RSS, but you won't find any RS in which plus charge is coming adjacent to oxygen atom. That is similarly, if you compare between the rates, this is a substituted, more substituted alkene where a 3-degree carbocation will be formed, as I have explained to you before. But this is an unsubstituted alkene, a butadiene, where a 2-degree carbocation is formed. These are two different substrates in different reactions. But if you compare the rate, here you find this is a 3-degree carbocation which is more stable, so the rate will be faster. And here this is a 2-degree carbocation which is less stable, so rate will be slower. And I have given you a lot of pairs in which you have to identify which one is more stable. And you can answer them very easily. You have only three things, minus I effect, minus R effect will destabilize a carbocation, and plus I effect and plus R effect will stabilize a carbocation, right? So answers also, and also this is a reaction where the carbocation will be formed, here or here, here or here. You can answer without any difficulty. The answer also I have given you. After you practice, you match with my answers. Now, then comes free radicals, carbon free radicals. Remember, oh, I have lost one dot. Remember that only in case of alkyl free radicals, the trend is similar to same as that of carbocations, because carbocations and carbon free radicals, they have one thing in common. The common thing between them, that both are electron deficient species. As if, the difference between the two is that the p orbital which will enter into conjugation or hyperconjugation, carries an unpaired electron in free radical, but it is empty in carbocation. That's the difference. Otherwise, both are electron deficient and behave similarly, but radical has some other features also. I will explain to you. Now that the 3-degree free radical is more stable, because hyperconjugation is the only effect which will explain why a 3-degree carbon free radical is more stable than 2-degree, then ethyl, any other 1-degree, then methyl, because there are 9 alpha hydrogen, 6 alpha hydrogen, 3 and none. Hyperconjugation is maximum here. And the resonance effect also can explain why benzyl and allyl radicals are stable and why benzyl is more stable than allyl. The electron delocalization of this unpaired electron is possible by resonance, pi electron delocalization. Similarly, the unpaired electron next to a heteroatom like oxygen and nitrogen, that is a lone pair adjacent to a unpaired electron. This unpaired electron to be treated like a plus charge. So you can have one electron shift, that is in all these cases, whether this or this, there will be one electron shift shown by a fish hook arrow mark. So there is a resonance here and there is no resonance here. Similarly, this is the only advantage, exceptional case, in case of radicals where you have a minus R group or minus electron withdrawing group, EWG, even then it will stabilize a carbon free radical. Had it been a positive charge, it would have destabilized the positive charge. But radical is not a positive charge, it's one electron. So other electron will come here and have a double bond here and one dot will remain here. I have not shown the resonance structure. That is why it is more stable than the one which has no such resonance stabilization feature. And similarly, like carbocations, the vinyl is less stable than ethyl, and ethynyl radical is least stable because this is p or s orbital, this is sp hybrid orbitals, and this is sp2. So this will be treated like a positive charge. The electron deficiency will be rather stabilized. It will be stabilized if it remains on a less electronegative atom. Same thing happens in a period. Of course, these are not organic, but I have thought of telling to you, in a period, the radicals also go on decreasing in their stability. While you go from left to right, the electronegativity increases, means the electron deficiency will not be stabilized with a more electronegative atom. Similarly, down the group, as the electronegativity decreases, the radical stability increases. Right? More is the electronegativity of the atom, less is the stability of the free radical, because it will be treated like a positive charge. Now, unlike the case of carbocations, which were judged on the basis of hydride ion affinity, here, to assess the relative stabilities of carbocations, we will take bond dissociation energy, BDE. Bond dissociation energy, more is the bond dissociation energy of the CH bond, less is the stability of the free radical produced after the bond breaks homolytically. After the homolytic cleavage of the CH bond, H dot goes away with some other radical, forget about it, and we get the carbon free radical. And if it happens easily by applying less energy, because HIA, the energy sign was negative, it is evolved. But here the energy sign is positive because it is absorbed to break the bond. So if a radical is more stable, then less energy will be required to break the bond in order to get a more stable radical. Therefore, you won't find the similar trend in the order that you found for carbocations. Now see the trend. Here in radical triphenyl methyl, there is no aromatic here. Triphenyl methyl is number 1, then diphenyl methyl, then 3 degree allyl, then benzyl, which is same as 2 degree allyl, then simply allyl. And allyl here is more stable than 3 degree alkyl free radical. If you are a foolish guy or a girl, you just apply the same trend that you found in carbocations in carbon free radicals, you are gone. You know, the method of determining stability is not HIA, it is BDE. BDE is positive and HIA is negative, so the concepts are different. That is just an addition of H minus ion with a positive charge to form a sigma bond, but here the breaking of a bond homolytically, not heterolytically. That's the reason why you find here the allyl carbocation, allyl free radical is more stable than this third butyl. You may wonder, you might ask me that here also there are so many hyperconjugation structures. But mind you, here there is one unpaired electron. Electron is there. There is a repulsion factor. In carbocation, it's an empty orbital. So the extent of overlap and delocalization was much more profound than in this case where there is one unpaired electron. Although we count the number of hyperconjugation structures is 10 because of the 9 alpha hydrogen atom, but each of them is not a very profound overlap. So because of the poor hyperconjugation in case of radicals, and here a real conjugation, resonance, allyl becomes more stable than 3 degree, then 2 degree alkyl, then any other 1 degree ethyl, then methyl, then vinyl, then phenyl, and finally it is ethynyl. In case of carbocation, methyl was coming just before ethynyl. Vinyl, phenyl, then methyl, then vinyl, then ethynyl, But here methyl, then vinyl. You can't say why there it was first vinyl, then phenyl, then methyl, and here methyl, vinyl, phenyl, and common thing is ethynyl is the last. Why this has happened here? You can't ask me. Because this is an unpaired electron, which is not the same as a completely loss of electron and having a plus charge. And I am giving you the supporting evidence so that nobody can challenge you that why you are saying this. It is because, you find this methyl, this CH bond breaking needs the maximum energy. This is the CH in ethane. So therefore the ethyl radical, after the homolytic cleavage you get the radical, methyl radical, ethyl radical. So ethyl radical is more stable than methyl radical because it needs less energy. Still less energy is isopropyl. Still less energy is a third butyl. But vinyl is 112. It is even less stable than methyl. I have already told you it is less stable than methyl. Ethinyl 133 is the least stable. Now phenyl comes here. Phenyl 110 and this is 112. So phenyl is little, oh my god. Phenyl is 110 and less the bond dissociation energy, more is the stability. So phenyl should be more stable than vinyl. So nothing has happened. To err is human and to rectify is also human. So give me a chance to rectify this order according to the data. First comes phenyl radical, then comes vinyl radical. Do you remember? Do you know that you have also another data here in terms of this is another source. This is in terms of kilojoules per mole. Vinyl is 452 and phenyl is 480. So oh my god, this phenyl is 112, which is more, and this phenyl is 110. Phenyl is 460, which is greater. So vinyl, yes, undoubtedly this is 460. So phenyl is according to this, phenyl is more stable than vinyl. But according to this data, this vinyl is more stable than phenyl. So I think in this controversy, I will give my ruling, my veto power is mine. I will again keep this, and I will rather say greater than equal to. I will be diplomatic to this. Although in one literature you find the BD data is saying that vinyl is more stable than phenyl, but here it is saying vinyl is, this one is less stable than phenyl. I accept this data. So then finally everyone is unanimous in making ethinyl triple bond. Data is not here. This is triple bond 133. Well, with this I conclude this session, accepting a controversy here, this greatering exceeding this or this exceeding this. All others are unanimous. There is no way to challenge and say against it. But this, yes, the data, they show different data. So my ruling is like carbocation, this trend is similar to carbocation. Vinyl will be more stable than phenyl, right? Bye bye. In the next video we shall be talking about the acid strength and base strength in general, using all our knowledge, and particularly carbon acids whose conjugate bases are carbanions. In this video I didn't keep carbanion stability order deliberately because that will be discussed in acids, relative acid strength and base strength. Automatically carbanions will come as their conjugates, and then we'll talk about the relative stabilities of carbanions. Bye bye.